Hello, this is part G of the Chapter 7 lesson. In this part we're going to introduce yet another type of hypothesis test that we call ANOVA. ANOVA is short for Analysis of Variance. ANOVA is going to be somewhat similar to a two-sample t-test in the sense that we are going to be comparing population means, but the difference here is that we're going to compare more than two population means. So to illustrate this, we're going to look at just one example. This is example 714 from the book. And in this example, researchers want to compare three different diets. We have a low-calorie, a low-fat, and a low-carb diet. Each diet is assigned to 5 different participants, and then 5 different participants are put on a control group. The weight loss after 8 weeks is recorded, and so that data is shown here. So the first person on the low-calorie diet lost 8 pounds, the second lost 9 pounds, so on and so forth. In the low carb, the first person lost 3 pounds, the second lost 5 pounds. Control group, the first two lost 2 pounds, the third person gained a pound, the fourth person didn't lose anything, and the last person lost 3 pounds. And so here's the data, and the question that we want to try to answer is there a significant difference in the mean weight loss among the 4 diets? So this is a question about means. We're going to be comparing population means. And so let's make an observation here, is that we're really comparing 4 different populations. We have all people on the low-calorie diet, all people on the low-fat, all on a low-carb, and then all those in a control group. And we're interested in these 4 different populations. We're not just interested in the 5 people on each diet. We're interested in really the populations of all people on a low-calorie versus a low-fat versus a low-carb versus control. And we're asking if there's a difference between these 4 different populations, specifically a difference between the 4 population means. And so our claim, or the research hypothesis, is that there is a difference. We're not claiming that necessarily one is bigger than the other. We're just claiming that there is a difference. So we have 4 different parameters for this test. They're all denoted mu because they're all going to be population means. Mu 1, 2, 3, and 4. Mu 1 is the mean weight loss of all those on a low-calorie diet. Mu 2 is the mean on the low-fat. Mu 3 is the low-carb. And then mu 4 is the control group. And as always, we include the word all in our definition in the parameters because we're making a claim about the large populations of all those on a low carb, on a low fat, and so on and so forth. So to set up the hypotheses, as always, the null hypothesis is the general statement that there is not a difference or not a change. And so in mathematical notation, the null hypothesis is going to be that mu1 equals mu2 equals mu3 equals mu4. The alternative hypothesis is the same as our claim that there is a difference. And kind of in more mathematical terms, we would say that the alternative hypothesis is that the means are not all equal. Maybe 3 of them are equal and 1 of them is different. Maybe all 4 of them are different. Maybe 2 of them are the same and the other 2 are the same, but they're not all the same. But in general, the means are not all equal. That's our alternative hypothesis. And the theory behind this type of test is very complicated. The book talks a little bit about it. Don't let the calculations in the book scare you too much because we're going to do all the calculations in Excel. The test that we're doing is called ANOVA, which stands for Analysis of Variation. And if we go to the workbook chapter 6 and the worksheet ANOVA, this is going to be a blank worksheet. It's because this ANOVA test is built into Excel. And so we're going to enter our data just like we see it here. And then we're going to go to the Data tab and choose Data Analysis. And we'll get a window that looks like this. And the first 3 options are for different ANOVA tests. The one that we're going to use is called ANOVA Single Factor. There's also 2 different tests for ANOVA 2-factor. This particular test is called Single Factor ANOVA, or sometimes called One-Way ANOVA. The single factor stands for the fact that our populations are distinguished by just one characteristic or one factor. In this case, the factor is the type of diet. If we had situations where our populations were distinguished by two different factors, like maybe we had a diet and a gender or something like that, then we'd use a two-factor ANOVA. But we're not going to get into two-factor ANOVA. We're just doing single-factor. So press OK, and then we'll get a window pop up that looks like this. So we're going to select our range of data. So we're going to select the data as well as the labels in the first row. Choose grouped by columns. That's because our data are in columns as opposed to rows. Check this, labels in the first row. Alpha is 0.05. That's always our default level. And then for output options, choose a blank cell for the output range. I chose F1, but there's really nothing special about cell F1. And you press OK, and Excel is going to crunch the numbers. You'll get a result that looks something like this. You may have to resize the columns in order to see everything, but we see this is the results from a single factor ANOVA. It gives two different boxes of results. The first is what it calls summary, and here it gives us simply the summary statistics of our 5 different samples of data, or 4 different samples of data. So for the first sample, the low calorie, we had 5 data values. The sum of those values was 33. The average of those 5 values was 6.6, and the variance is 5.3. Remember that the variance is the square of the standard deviation. And so you see the averages for these 4 different samples. And we can just kind of compare these averages informally, and we see that this first average is quite a bit larger than all the rest. This last one is quite a bit smaller. And so the fact that these averages are all different is an indication that our populations are not all the same. And so the fact that these averages are different would cause us to maybe want to reject the null hypothesis. But whenever we compare sample means, we need to compare we also need to take into account their sample variances or sample standard deviations. And so we've got to take these numbers into account as well. And that's the basic idea behind ANOVA. It compares these sample means, but also takes into account the standard deviations. And down here it gives all the results. There's this number here, F, is the test statistic. These numbers over here, SS stands for sum of squares, MS is mean squares, DF is degrees of freedom, and there's different categories. These numbers are all used to calculate the test statistic. We won't get into that here, but it also gives a p-value and then a critical value. If we wanted to use a critical value method, then we could compare this critical value to the test statistic, and that's kind of what the book does. But we're not going to do that here. We're just going to look at the p-value, p-value 0.00127. So we're going to interpret that p-value just like every other hypothesis test. We're going to compare that number to the significance level 0.05. In this case, the p-value is less than 0.05. And so our conclusion is to reject the null hypothesis in favor of the alternative. And so we would reject the statement of no difference and favor the statement that there is a difference. And so we would interpret this by saying that there is a statistically significant difference in the mean weight loss among the 4 diets. So there does appear to be a difference between the mean weight loss of these 4 diets. So now the next question we might ask is, well, just which diet is different than the rest? And we can informally answer that question by comparing our sample means, as we did a minute ago. We look at our sample means right here. The low calorie had the highest sample mean. The control had the lowest sample mean. These two were about the same. So this is an indication that mu1 is bigger than all the rest. It looks like mu4 is less than all the rest. mu2 and mu3 are pretty close together. But remember that these numbers here are just estimates of the respective population means. This is an estimate of mu1, an estimate of mu2, mu3, and mu4. So informally, it looks like mu1 is the biggest, mu4 is the smallest, mu2 and mu3 are pretty much in the middle. So that gives us an indication as to which diet has the highest mean weight loss and which diet has the lowest. So that's a very informal analysis. We can do more formal approaches to answer this question, but that's beyond the scope of this class, and so we won't get into that. So ANOVA simply tells us that there is a difference between the population, or there isn't a difference. The ANOVA test in and of itself doesn't tell us which diet or which population is different than all the rest. So it does have its limitations in that respect. So let's kind of briefly summarize this ANOVA test. The purpose is to compare the means of 2 or more independent populations. Typically, we only use ANOVA for more than 2 populations. If we have just 2, then we can do the 2-sample t-test. But ANOVA can be used to compare any number of independent populations. Like with the 2-sample t-test, our populations have to be independent, meaning what happens to one population has no effect on the other. The hypotheses are the null is that the means are all equal, or stated in other terms that there is not a difference between the populations. The alternative is that the means are not all equal, or in other terms that there is a difference between the population. And our requirements, we have 3 requirements here. The first 2 are what we call loose requirements, meaning that they don't have to be met precisely. Just as long as these requirements are not too far from being met, then they're okay. Number 1, the populations are all normally distributed. Again, we see this requirement of normally distributed when testing a claim about a population mean. Number 2, the populations have the same standard deviation. This is the same requirement as for our 2-sample t-test. And then the third requirement is that the samples are random and independent. Now, this is not a loose requirement. This has to be met. As always, we have to have a random sample, and we need independence. If there's any indication that what happens to one population has an effect on the other population, then this requirement is not met, and we got to do a different type of test.